think of.
Okay, Professor.
Okay. Okay. So we start. We're live. We're being recorded. And it's a great pleasure to introduce Eduardo Peinado from UNAM. He will give us the next talk about neutrino physics, dark matter, and UN symmetries. He's originally, I guess,
Okay,
from...
Professor.
Yeah?
Okay.
Okay.
Okay. So
Oh, I'm
start.
sorry.
We're
I have the...
live. We're being recorded.
Silence. Okay. So he's originally from Mexico, got his PhD from the university where he's now a professor, and had postdoctoral stays in Trieste and Valencia. So thank you, Eduardo, very much. And then I'll let you know when there's urgent questions, if they're appropriate, or when you have 5 minutes to go. Thank you.
Okay. Thank you very much. So I would like to thank the organizer for this kind invitation. I hope to see you soon in Brazil, especially to Orlando Perez for the invitation. So I will talk about neutrino physics, dark matter, and U1 symmetries. And this can be quite general because we have a U1 symmetry that can be global symmetries like the Pesci queen, or local symmetries like U1 B minus L's. So in several things, it will be kind of general because you can apply these kind of things to all of them. If I have time, I will also show one thing for Pesci queen. Otherwise, I will concentrate on a global and local U1 B minus L and different flavor extensions of this U1 B minus L. That you can have also anomaly-free solutions for B minus 2L alpha minus L beta, for instance, or U1 B minus 3L alpha, where alpha and beta stands for any lepton flavor. Okay, so the idea is to how to connect neutrino physics with dark matter using these symmetries. And there are different ways. One is to connect the stability, for instance, of the dark matter with neutrino physics. Also, you can connect dark matter with neutrino physics in several ways, not only for the stability, but through the mechanism for generation of neutrino masses. You can also connect with baryon asymmetry through leptogenesis, either for Majorana and Dirac. And what I will also show is that you can connect also one of the questions that need to be answered between, the neutrino sector, that is the nature of neutrinos, if they are Dirac fermions or Majorana fermions. Okay, so you can also play with that, given one U1 symmetry that can be global or local, giving you the stability of dark matter, and also telling you what kind of fermions are the neutrinos. Okay, so with this connection, there are several ways. Also, you can have sterile neutrinos playing the role of dark matter, warm dark matter. You can also have majoron or axions if you connect the Pesci queen with the neutrino mass generations. If someone wants to have a question, please feel free. Okay, so we know that neutrino are massive particles because they oscillate when you produce a neutrino with a certain flavor, like electron neutrinos or electron antineutrinos in the case of reactors, for instance. There is a probability that this neutrino change the flavor. You have the probability to detect, instead of an electron neutrino, if you produce one of them in either in accelerators or in nuclear reactors, and you can detect instead of electron or mu neutrino, if you produce one mu, the other flavor. Okay, so this is the proof that neutrinos are massive particles. Okay, so it was proposed several years ago by Pontecorvo that neutrinos can oscillate from one flavor to another in a similar way at that time of meson oscillations, right? it was an oscillation between meson and anti-meson. In this way, neutrinos, if this is the case, that neutrinos are not the eigenstate of interaction, the weak eigenstate, are not the eigenstate of masses eigenstate. So that is the way they can oscillate. So there are two conditions. One is that the eigenstate are not the same for masses eigenstate and interaction eigenstates. And the other one is that they are not degenerate. That means that the difference between the masses, squared masses, is not zero. So this is the case for two flavors. This is very, very easy to see. And in the case of three flavors, that is the case in the standard model, you have not one mixing angle, but three mixing angles, like in the quark sector, and two square mass differences. That means that at least two neutrinos are massive states, okay? So what do we know about neutrinos? That, as I mentioned, they are neutral, they are massive, with very light masses, but massive at the end of the day. There is a hint that they also violate CP in the oscillation. Like in the quark, we have the delta in the CKM matrix. We also have a delta CP in the neutrino sector. If they are Dirac or Majorana, we don't know yet, but if in the case of Majorana masses, you also have Majorana phases that the oscillations are not sensitive to those, but they could play a role in phenomena like the neutrino-less double beta decay, okay? That you have double beta decay with neutrinos in the final state, but if they are Majorana particles, there is the possibility to detect this process that is with no neutrinos in the final states, okay? So that will be the proof, according to the black box theorem, that if we detect this process, that will mean that neutrinos are Majorana in nature, okay? So what we know is that neutrinos are massive, but the masses are very light. If we compare with the fermion, the charged fermions in the standard model, like electrons and quarks, okay? So leptons and quarks. The lightest fermion we have that is charged is the electron, that is of the order of MeVs. And if we compare with the current limit by Catherine, it tells us that the effective mass for the electron neutrino is smaller than 1 electron volt. And if we take the cosmological limits that we have, neutrinos are even lighter than that, because this is the sum of the three light neutrinos that should be smaller than, it depends on what they combine, 12 electron volts. That means that they should be smaller than 0.04 electron volts, right? So they are very, very, very light, okay? So this is the picture of the global fits. I mean, if we combine all the experiments for neutrino oscillations, we have three mixing angles, and those are the range of the parameters at 3 sigma, or the best fit values. For the atmospheric mixing angle, that is big. I mean, is of the order of 0.5, the square, the square of the sine of this angle. And the solar mixing angle is also big. It's like 0.3, more or less, the square of this. And the smallest is the reactor mixing angle that several years ago, it was compatible with 0. Now we know that is non-zero at more than 9 sigmas, we know that. And the smallest one is of the order of lambda K vivo for the quark. So the smallest one in the neutrino is similar to the biggest one in the quark sector, okay? So we also have a CP violation that the phase now is in here. And if we see the 0 is not longer is not longer valid at 3 sigma at least, according to T2K. Now there is some discrepancies now with the T2K but ANOVA, but this is something that I will not discuss. But I mean, it seems to be the case that CP violation in the neutrino oscillations is non-zero. So there is CP violation there. And we have 2 square mass difference. The neutrino oscillations is also sensitive to the square mass difference of the neutrinos. We don't know what is the actual scale of the neutrino masses. So what is the mass of the lightest neutrino, for instance, okay, to set the origin. Okay, so there are three ways to test neutrino masses. One is through the beta decay, like Catherine is trying to set limits on the effective mass for the electron neutrino. Another one is neutrino less double beta decay if neutrinos are Majorana particles. It is also sensitive to neutrino masses and also to the Majorana phases. And from cosmology, which is the stringest bound we can get right now for neutrino masses, that is sensitive to the sum of the 3 masses of the light neutrinos, okay? So we can plot the lightest neutrino versus the cosmological bound, for instance, and we have for normal hierarchy, that is this line, and for inverse hierarchy, and cosmology is going down in the limits, okay? So we can also plot, for instance, the sum of neutrino masses from cosmology versus the effective mass parameter from neutrino less double beta decay. This is the region, allowed region for normal hierarchy, and this is the allowed region for inverse hierarchy. And we see that there is a region where, even though neutrinos could be Majorana, this process can be also negligible due to the interference with the Majorana CP phases. Okay. So the idea is to combine those to get some information. So if we compare, this is the CMS results from the last year, 2020, and we see that this is the mass of the particle versus the Higgs coupling, and we see that it is incredible the agreement of the experiments with the standard model, even for the muon lepton, which is light, if we compare with the top, for instance. Okay, so those are the masses for the charged fermions, and as we see, they range from half MeV to 100 GeV for the top. So this is the lightest charged fermion. And the point is that neutrinos are very light. If we compare with these, which they are, there is a hierarchy between the first, second, and third family of charged fermions. But if we compare the neutrinos, they are really, really far away from this scale. So neutrinos are more or less in here. In the case they are Dirac particles. That means that we are talking about couplings, Yukawa couplings for Dirac neutrinos of the order of 10 to the minus 13. Okay, so the other question is, are there Dirac or Majorana? So how can we get, or how do we get fermion masses in the standard model? Is through the coupling with the Higgs, because for the gauge symmetry, those masses are forbidden, but with the Higgs mechanisms, we, besides having the gauge boson masses, we also generate fermion masses, okay? But for the neutrinos, we can also have Dirac masses, or we can also have Majorana masses, since they are light. So this is also forbidden by the symmetry, but with the Higgs mechanisms, we can generate neutrino masses at dimension 5. So non-normalizable, but this is what Weinberg did in classifying this operator, the effective operators. He realized that this operator is dimension 5, and this violates lepton number in 2 units. So if that happens, neutrinos are Majorana, we can effectively generate this mass with 2 Higgses. This is dimension 5. So this scale, if it's very high, can explain why neutrinos are really, really lighter than the rest of the fermions. But if this happens, this process or this term in the Lagrangian violates lepton number in 2 units. And if that happens, what we can have is the possibility to have neutrinoless double beta decay. So there is a one-to-one correspondence. If you detect this process, that means that neutrinos in nature are Majorana particles. And if you don't detect that, it means that either they are Dirac or you are in the region that I show that where you have the cancellations. Okay. So there are different ways to generate in the context of the standard model this effective operator. One is this is the Dirac, the Yukawa coupling, like where you have a doublet of SU2. Remember that doublet times doublet gives you singlet and triplet constructions for SU2. So you can have one singlet of SU2 with the lepton doublet, the Higgs doublet. You could also introduce, instead of a singlet right-handed neutrino, introduce a triplet of scalar. That is the type 2 seesaw. Or you can also have what we call type 3 seesaw, that instead of adding a singlet, fermionic singlet, you add a fermionic triplet. Okay. So diagrammatically, what you generate is a dimension 5 Weinberg operator, 2 Higgses, dimension 5 Weinberg operator, 2 Higgses integrating out these heavy states, and the dimension 5 Weinberg operator. Okay, so if we add 3 right-handed neutrinos, this can be bigger, but let's assume we add 3. This is in the left-right neutrinos. This is the entry coming from the type 2 seesaw with a triplet. Those are the Dirac mass terms, and this can come either from type 1 or type 3. There are other light seesaws like the inverse that I will not mention here, and there is another way to generate this dimension 5 Weinberg operator that is at 1 loop or more loops. Okay. So now let me talk about the stability of dark matter. We know that we live in a universe with a lot of dark matter. That means that basically it doesn't interact with photons or through electromagnetic interaction. And the easiest thing to have a stable, it can be very long-lived, but it's easier to speak about stable dark matter. The easiest way is to have a symmetry protecting these new particles from the decay. Like in the standard model, we have, for instance, baryon symmetry, that is accidental symmetry in the standard model, but provides the stability of proton. So you can have either a symmetry protecting this dark matter from the decay. It can be a genuine symmetry, like any symmetry you can think about, like QED, for instance, U1 of QED, or it can be an accidental symmetry coming from other symmetries, like baryon symmetry in the standard model. Okay, if we focus on this genuine can be local or global symmetry, or it can be a residual coming from a local symmetry, as I will talk later, which is the main thing of my talk, actually. A gauge symmetry that gives you stability of dark matter, and you try to combine different observables to put constraints, to set constraints. Okay, so you can also have global symmetries with that breaks and gives you a residual symmetry. That is the case, for instance, for the Pecha equation. If I have time, I will show an example of that. Okay, so let me go fast. How does it work? The U1 symmetry, basically, this is the symmetry U1 is a continuous symmetry in the circle, and it can have several. Actually, it has several residual symmetries. For instance, a set 2 symmetry, where you have only these 2 points. There is a parity. You can also have set 3 symmetry or set n symmetry. So since you already have ways to have residual symmetries coming from U1 symmetries. It can be useful for dark matter stability, or it can be also useful to tell us how in your framework neutrinos are, in the sense of if they are Dirac particles or Majorana particles. Okay, this can be global or local. This is general. And how does it work? For instance, let me show a toy example. You have two scalar fields, one transforming as minus n and the other one transforming as m under this U1 symmetry. If n is bigger than m, what you have is that basically you have this kind of terms in the potential. For instance, if this is 2, n is equal to 2, and m is equal to 1, then you will have phi squared and chi. If the chi acquires a bev, then you break the symmetry into a residual set 2. Okay, and this is the way you can play with this. Of course, if you include fermions in this framework, it will be more complicated, but more or less is similar. Okay, you can also have extra accidental symmetries there. If we focus in U1b minus L, that is already present in the standard model, the way you break U1b minus L will tell you if neutrinos are Dirac fermions or Majorana fermions, depending on the way you break this symmetry and the way leptons transform under this residual symmetry. Basically, if this M is odd, that means that you will have Dirac neutrinos, and if M is even, it will depend if M is equal to 2n, if leptons at the end of the day transform as n, that will be Majorana, or if they don't transform in that way, they will automatically be Dirac fermions. Okay. For three right-handed neutrinos, there are two anomaly-free solutions that you can use in order to promote this symmetry to be a gauge symmetry. One is the normal one that the right-handed neutrinos are -1 under B minus L, or the other one is -4, 5, which automatically forbids the Dirac mass term directly. Okay, that means that if you want to generate this kind of operators in the Lagrangian, you have to move to dimension 5 or higher dimensions. Okay, so in this way you can generate somehow this 10 to minus 13 Yukawa coupling for Dirac neutrinos in an effective way. And you can use either type 1 Dirac CISO type. I mean, you can play with the topology of that, but you can also use loops in order to generate the dimension. In the case that you generate this at dimension 5, in very similar in the way that you do it for Majorana, but this is for Dirac. And then everything inside the loop can be in the dark sector if some requirements are fulfilled. That means that those particles, at least the lightest particles in here, should be stable. Okay, in that way you can have from this U1b minus L, in this case, you can also extend this not to B minus L, but to other symmetry. You will have the nature of neutrinos, either Majorana or Dirac, effectively generating in a natural way the Yukawa coupling for Dirac neutrinos, small in the sense that you can do it at 1 loop or even 2 loops or 3 loops, and have dark matter stability. So without imposing extra symmetries in your framework. Okay, so dark matter stability works when you have the set is even. That means that you can apply this for Majorana and for Dirac. because when you have this set M residual symmetry that is even, if you have a field that transforming as odd power of this set M, basically omega is in this case is the 6th root of 1. It will be the M root of 1 in the case of M. If this is odd under this symmetry, the conjugate field will be also odd. That means that you can use that in the way that will give you the stability of the dark matter, and that is crucial. Mostly because if you have a scalar field and it's odd under this symmetry, the conjugate of the field will be odd as well. That will not happen when the set residual symmetry is odd. Okay, so you need to be in this sets 4, 6, 8, whatever, in order to get the dark matter stability. Okay, in this way, if anything inside the loop or in this sector is odd under this residual symmetry, and the standard model, mainly the leptons, are even under this symmetry, there is no way for this dark matter to decay. Okay, and for Majorana, you can see this paper. You can extend this idea to n loops, and if the standard model leptons are even powers of this symmetry, the dark matter can be either fermion or scalar inside this loop, provided that they are odd under this symmetry. And if the standard model leptons are odd under this symmetry, it can be the scalar dark matter that transform as odd, or the fermion inside the loop can be the dark matter if they transform as even. And this is because you play a bit with this symmetry and Lorentz symmetry. Okay, basically this is the recipe if you want to have dark matter also coming from this residual symmetry. Okay, so let me focus now in the case of a gauge symmetry. Okay, if you have a gauge symmetry, this is U1 prime, and I'm not talking right now about the standard model, but what you have is basically that you will generate a mass for this vector boson by spontaneous symmetry breaking of this symmetry with scalar fields, and you will couple these gauge bosons to the fermions. Okay, so what I want to focus is in light vector bosons, because I was interested in sevens, I mean coherent elastic neutrino nucleus scattering, because those kind of experiments can constrain light vector bosons in a complementary way from colliders or other kind of experiments like dim damp. So in this way, the mass of the set is basically coming from the BEP of the scalar fields. Okay, so for light vector bosons, either you have a small coupling, you have a gauge coupling, or you have a low breaking scale. Okay, so if the standard model, if the quarks in the standard model are charged under this symmetry, you will have a coupling of the nucleus with this set prime. And if the leptons are also charged under this symmetry, then you will also couple charge fermions and neutrinos with this scalar. Okay. So now let me move a bit to the sevens experiments or the seventh process. It was already detected in two different targets by the coherent collaborations. What you have basically is in the spallation neutron, they have muon neutrinos and muon antineutrinos and electron neutrinos. Okay, and basically this is the flux. Basically they have a monochromatic muon neutrino, and they have also a profile in the flux for the antineutrinos of the muon and electron neutrino. Okay, so what happens here is that the energies are below 50 MeV, and it interacts coherently with the nucleus. In this case, for iodine cesium, they detect 134 events in 300 days. And for argon, they detect 159 events in 240 days. And they are taking data with argon, okay? So if we compare the flux of the neutrinos in the spallation neutron source with a reactor, and this is the reactor flux with this power. I mean, this is a very small reactor neutrino, a trigger reactor of 1 megawatt thermal. And you place one detector at 3 meters, it will be the flux that if you compare with this flux is several orders of magnitude bigger. Okay. Right now there are several proposals, and actually there are also a couple of more than a couple of experiments going on. One actually is in Brazil, the CONI experiment, trying to detect this process. Okay, so this is the table that you can look at this paper where they tell you the power of the reactor they will or they are using or they will use. And what we did is to check 2 different reactors for scintillating bubble chamber detector, just to see, just to give you the numbers. This detector, one of 10 kilograms, is under construction right now by the SBC collaboration. Actually, they are building 2 detectors, one for dark matter that will be located at Sudbury, and the other one for detecting sevens. Okay, and we did 2 analyses. One using a trigger reactor of 1 megawatt thermal power, and the other one of 100 kilograms that will be in the future in case of they build it for 2 gigawatts thermal power. So at 30 meters. So in this case, that this is the detector that is under construction. We are sensitive to 8 neutrinos events per day. That means that in 1 year, we are talking about almost 3,000 events. So several events more than was detected by the coherent collaboration. And if you place in this more powerful reactor at 50 meters, we are talking about orders of magnitude more events per day. Okay, with that you can constrain precision measurements for the standard model, like the weak mixing angle. Those are the 2 setups. Actually, in these 2 setups, we use I think it was like 2.5 uncertainty in the reactor flux. That is the main uncertainty we have. And using 1.5% of uncertainty in the reactor flux, you reduce this. And this is let's say the most optimistic we could have. That is what that was measured by the Diabay collaboration. You could also have constraints on magnetic moment of the neutrinos, which is not as competitive as Borexino, for instance, but is in the same order of magnitude. But you can also constrain like vector bosons. Okay, as I mentioned before, Siemens experiments are very good in very light masses, and is let's say complementary to the searches in colliders. Okay, this is for the U1 B minus L, but you can extend to B minus something in L. You can play a bit with this and include flavoring in the leptonic sector. Okay. And the point is that as I mentioned before, now it is very easy for us to include dark matter without imposing extra symmetries or extra stuff, just only adding one particle that interacts or is charged under this U1 symmetry. And if this new particle is charged under this symmetry, then you will have effective coupling of the dark matter with the nucleus. And you can also have a correlation because you will use this new interaction in order to get the correct relic density in the early universe. Okay, so this is the Lagrangian basically. If the charge of this fermion is 1/3, that means that it will be a Dirac fermion. If the charge of this is very similar to what we did for the neutrinos, if this new fermion is charged with 1/2, then you will have a Majorana dark matter. Okay. And also the neutrinos will be Dirac or Majorana depending on the way they transform, as I mentioned before. So for the dark matter relic density, what you have is this S channel, and you also have this T channel. So since we are looking at very, very small couplings, you need to effectively annihilate this dark matter in the early universe. So what you need, or what we need, is a resonant annihilation that sets you a correlation between the mass of the new gauge boson and the mass of the dark matter, okay? Which is good because it gives us a correlation, and then we relate these two parameters that in principle are not necessarily related, okay? So as I mentioned, you can have Dirac fermion for dark matter or Majorana fermion for dark matter. And there, different things could happen. For instance, you can also have an extra channel for the annihilation of the dark matter in the early universe. So we lose this nice correlation for the resonant annihilation. So we focus on the Dirac case, okay? So by doing that, as I mentioned, you have this channel for relic density, but basically is what the only thing that changed from this and this is the coupling is the same, and what changes are the charges of K's and the dark matter and the fermions in the standard model. And now this is the interesting thing, is that the dark matter direct detection and the 7 processes are basically are very similar, because you have the gauge coupling that is the same for both, and the only change is the charge, okay? That this is 1/3, and it will depend on the model you are looking at, okay? So we analyze this case, the U1B minus L, but you can extend to several different charges for the leptons, provided that they are anomaly free, of course. So if we, for instance, analyze this solution that alpha and beta are different flavors, what you have is that on top of what I mentioned before, you can also have predictions for or correlations in the neutrino oscillations, because not all the couplings are allowed. So you need at least 2 different scalar fields that breaks this new symmetry in order to generate correctly neutrino masses. And what you have is this kind of predictions. Basically, what we analyzed, it was the 6 possible solutions. 4 of them are in agreement with the current oscillation parameters. And as you see here, either you have the muon and tau that are charged under this, or electron and tau and electron and muon. So if you analyze, for instance, in the coherent experiments, they have electron and muon flavor. So they can constrain this, they can constrain somehow this, actually the 4 of them, okay? But if we look at what we can have from reactor experiments, you cannot constrain these 2, because for reactors, what you constrain is the electron flavor, okay? So what we check is that these 4 are in a good agreement, and actually, since in the model, the fermions are, charged fermions are already diagonal. this 1 element is basically the effective mass for the neutrino less double beta decay. So in these two cases, you have a 0 neutrino less double beta decay, at least at 3 level. And in these two cases, neutrino less double beta decay is non-zero. So these two are with 0 neutrino less double beta decay, even though neutrinos are Dirac, Majorana. And in these two cases, the neutrino less double beta decay is actually quite big. Okay, so in one case is very, very almost in conflict now with Campbell-Sen. In the other case, it depends on the nuclear matrix element in here, but also Campbell-Sen is almost ruling out these two scenarios. Okay, so this is a benchmark. For instance, if we break this U1 B minus 2L minus L beta at the TB scale with a gauge coupling of 10 to minus 5, then you have the new gauge boson of order of 0.1 GeV, okay, more or less around here. This was the projection of the Conus experiment. And when we translate this to other scenarios like B minus L, B minus 2L alpha L beta, and we also check the one that was not in agreement with the experiments, you can somehow save these two scenarios by including a third scalar. So this is, you have predictions for neutrino oscillations. In this, you have one prediction instead of 2 zeros, you have 1 0, one correlation. And these two cases, you don't have any correlations for neutrino oscillations, but you have the rest. I mean, you have dark matter and you have dark matter direct detection. And as I will show in the next slide, you have a correlation of what you can prove with the SEMEX experiments and what you can prove from the direct detection experiments, okay? So for instance, this is the U1 B minus L scenario where all the leptons transform as -1 of these gauge bosons. Basically, the coherent cesium and also the argon is more or less the same. And constrain all this region. I mean, this region is excluded by the SEMEX experiment. This is excluded by Babar, LHCb. We can translate all these constraints to the dark matter direct detection plane, where you have xenon, etc. You have the neutrino fluorine here. And when we translate this in this scenario, for instance, coherent is going in here, Babar is excluding all this region, and the forthcoming SBC collaboration of this the case of the 10 kilogram, the one that is under construction, will reach all this part that will constrain all this area. What is interesting here is that the current experiments for data detection are basically insensitive to all these areas. So you can, in these kind of scenarios, make the interplay of that, okay? So all the white part is the allowed region. And this is the flavorful model, so, okay? So in this case, you have the electron. So you also have SBC and 7s. In this case, you don't have the electron that is charged, so you only have a 7s experiment constraining this panel. So you can translate the 7 experiment to this panel. That in the future, this will go a bit down, so it will constrain further this part. And also the other two cases that they were ruled out with 2 scalars. If you include a third scalar, then you also have constraints on that. And the case of 3L tau, 3L mu, in the 3L tau, you don't have any constraint coming from 7s because we don't have access to the mu and the tau flavor. But you can also have neutrino oscillation that can give you constraints on that. Okay. So with this, I conclude. I don't know if there are questions. I can also mention the part of Pechi-Quinn if someone, I mean, how this thing of the Pechi-Quinn can give you at least the nature of neutrinos and how you can more or less combine the searches for the coupling of the axion with photons and the neutrino masses. But let me conclude this part at least, so that this is very easy to incorporate dark matter in any U1 symmetry, gauge or global. And if you charge different flavors of leptons differently under this U1, then you also have correlations at least for the oscillation parameters. And there is a complementarity between the dark matter searches, colliders, and Sevens experiments in the case that the dark matter is charged under this U1 symmetry. So, muchas gracias.
Gracias. So whoever wants to open your microphone and applaud, I think is able to, but for 90-something people, I don't know. I guess not everyone. Yeah, there's also a reaction button. So thank you, Eduardo, very much for this very nice talk. We still have time for questions. I don't see any written questions either in the chat box or the YouTube box, but you're free to raise your hands and open your microphones and your videos. So there's a few reactions of this plot. I don't know if you can see it, Eduardo. So, well, if anyone wants to open the microphone and is not able to, just let us know. You have mentioned a few, ongoing and under construction experiments, new experiments. I understand this is a very exciting time that you're expecting to have answers to all these questions. Can you put some time frame or expected? Like
yes.
if it was next year, would you be able to answer some of these questions?
Well, with this thing of the COVID, I think, I mean, this right now is under construction by the SBC. Okay, they need to calibrate really the threshold, because we are talking about a very low threshold detector that is 0.1 kilo electron volt threshold. But in principle, my guess is that is maybe in 2 years, it will be just to build and very well known the threshold and all that things to put in this reactor at least. So let's say that in 2 years, and this is very exciting because there is a race in this sevens for reactors, because Conus and Coni in Brazil, they already have run the experiment and they didn't really detect any event. So everything was consistent with the background. So everybody wants to detect this in the first time. So there are several proposals and several experiments going on, some of them going on and some of them are proposals, right?
So in a 2-year time frame, you should have some
very
different view of what you presented. That's very exciting. I don't know, maybe for the young students, I mean, can you name maybe some of the models or ideas that you think are more at risk? Like if you were to pick a subject for a thesis, this
well, in general, sevens is right now a hot topic, because you can put constraints in electroweak precision. You can also test new models. I didn't mention, but you can also test what we call non-standard neutrino interaction that is encoded in this effective Lagrangian. But if neutrinos have non-standard neutrino interactions with matter, then you will also somehow constrain these models with these experiments, of course. I didn't show the NSI parameters here. You can constrain with these experiments, but it is something else that you can do. I mean, several new physics scenarios that you can constrain with these experiments. And right now, I mean, coherent experiments also taking more data. So,
all right, thanks. Very nice. Is there a question?
well, I see
Yuri,
there is.
Yuri, if you want to open your microphone. Or your video, or if you want to just write it in the chat, we can read it for you, or you can also write it in Portuguese and we'll translate. Judy Gomez, you raised your hand. All right, then Manuel, and then we'll wait for.
Hello. I'm here. Hi, Eduardo. Nice talking. Thanks for the nice talk. I only know about the possibilities in the dark matter sector. We don't know what exactly is dark matter. So what about the possibility to try different vertex interaction, derivative vertex? There is some process involved this kind of possibilities.
Well, there are, I mean, this is an open question, right? What is the mass of the dark matter candidate? If that is a WIMP or not, if that is, it was freeze out or freeze in, or even the axion could be the dark matter candidate, right? And for the axion, there is no way to make a direct detection. What we do for the axion is to search for couplings with gammas, for instance. That was the other thing that I wanted to show, but for time being, I couldn't. But when you have the axion, there is a pseudo-scalar field. What you put constraints is on the effective coupling of the axion with photons, right? And that tells you more or less the scale of the Peccei-Quinn breaking symmetry. But if somehow you can relate this to neutrino masses, you can also combine the current limits on neutrino masses to put a limit on this span. And this is, I mean, this is for the QCD axion, right? If you have an axion-like particle that is not related at all to the QCD, then is anything here. But this is another kind of dark matter that is you can constrain from different either experiments or different observations for astrophysics. But sure, if you have some other candidate, it can be fermion scalar, it can be charged under the SU2 or not. So it depends on the dark matter candidate you have. Yeah.
Thank you. Does that answer your question, Manuel? All right. So
Yes.
Okay, thank you. Carlos, do you want to ask your question? Or I think he maybe raised his hand by mistake. Anyone else? Well, I don't see anyone. Let's see in the YouTube channel. No. And then here in the chat, no. So I guess Carlos and Yuri, please excuse me if it was because you raised your hands. I guess it was by mistake. But if there are no other questions, then I think we can all join in thanking Eduardo for a great talk. And please feel free to unmute and thank our speaker. Thank you.
Thank you.
Thank you. So we hope to meet again soon in a in-person meeting.
I hope so.
Bye-bye.
I look forward. Ciao.
We're still streaming, I think, and I sent you by